don't care about that, except for the fact that I I have to do that and go and visit her. So in so doing, I give quizzes, and I have 4 courses, and I got the wrong quiz for you. If everybody recognized that, that's good, because you do not need to know how to do Laplace for this course. You all did it dutifully. Some of you probably with ChatGPT, others probably did it honestly, and I don't really care. But these are not going to get graded, okay? Quiz 3 is going to go in the trash bin, and that's the end of that. Okay, if you wondered about it, whether or not this was for this course or not, if it's a joke, I meant for you to have a quiz, but the one that I sent you last night was the one that I actually printed out for you, and I'll work it tonight, free. You don't have to hand it in. There's no quiz 3 at all, so this will be this is not a joke. I just picked the wrong one. So this went to another class. Also, I picked it for you guys. Nobody asked me, or nobody said this is the wrong quiz. That's kind of interesting, because you must have thought that I really want to require this in this course. Nope, I'm not. So you can relax on that. All right. Sorry about that. All that being said, being passed around of what I have graded, I want to go through a little bit about what's some of the things that you can be working on now. I want to do that tonight. All right, so let's look at that quiz for just a minute. It won't take more than a minute, but let's look at it so we can get it out of the way. So this is the quiz I want you to take today. It was really on Tuesday or over the weekend, and this is really not hard at all, but it is a little bit more difficult. I wanted you to see that it's a little bit more difficult than some of the ones you've done before, but you can look at it and you should be able to do it without having to go through and rewrite it or anything like that. But you may end up wanting to rewrite these, and then that's up to you. But anyway, I want you to understand that this is not a big deal, but I wanted to be able to go through it. So look at this one and you say, okay, so it's this or this, so it would be the knot of A anded with D. That would take care of that. Now this was anded, so now it is ORed with all of this. And that has this anded, so now it would be ORed. So it would be D, B or E, so it would be now B naught and E naught. And it was anded, so now it is ORed with D, or with C, excuse me. Okay, so this would be, ORed with this, yeah. B and, okay, ORed with the, anded with the knot of, anded with C, and it was ORed, now it is anded with the knot, with F. You bring it back together, and now you have the knot of G. Is that right? Hopefully. Did I do that right? Maybe. Any questions? Any comments? A or D is now A naught and D. B naught or E naught is now, or B or E is now anded of B naught and E naught. ORed with, anded with C is now ORed with C, and then was ORed, now it is anded with F. That's G naught. Any questions about that? Can you do that with your eyes closed or your eyes open or whatever? Good. All right, so I want to go back and review just a little bit about the syllabus. The syllabus. We are for 5th week of the course, and we're now thinking about what we're going to do for a midterm and all that good stuff. But I don't want to go too close into that yet, but I just want to get you aware of a couple of things that are on the syllabus, because I am going to modify this a little bit down the road for other projects that you can do, but this page right back here um, is very, very, very important, because it gives you the lab numbers, and that's how you turn these in by. Please identify a lab by that number, okay? When you turn in a lab, identify it by that number. Now, there are 2 labs that you can do for each of these. You can do at Allen Bradley, you can do at Siemens. So you can do up to 20 points of these 2-point labs early on, and you can pick off a lot of these. You can pick off 4.1, you can do it with Allen Bradley and Siemens. You can do, that's 4 points if you do both. 5.1, you can do it both ways, Allen Bradley and Siemens. Now, can you come back and do it without the HMI and then do it with the HMI? No. Once you've done it with either the wiring or the HMI, you can't go back and get 4. You can't double dip twice. You can get the Allen Bradley and Siemens, but you can't get Allen Bradley and Siemens with wired and an Allen Bradley and Siemens with the HMI. You cannot do that. You either have to pick the HMI or the wired, and I encourage you to pick the HMI approach, okay? Because it's faster. Once you catch on to how to do the HMI, it's faster, and you're not having to rewire every time, because somebody's going to come in after you and mess you up, and that's a fact. So if you come in and get it done in one setting, it may take you a little bit longer the first time, but once you've established that you can do the HMI portion of it, you're in good shape. I would encourage you to use the view from Allen Bradley, not the factory talk. And with Siemens, it's pretty straightforward. They're all in the same, they're all in the TIA program. But with Allen Bradley, it's a little confusing, because you flare off immediately to go to Logix, or you go to View. Now the key with this is to save this program, and then this one identifies where that's saved, and it goes and gets those variables, okay? But you have to save it first. You have to do a save of the Logix program before you can get the variables from the view. This program from the Allen Bradley is pretty crude, but it's better than about anything else right now that we have. We also have this program called Factory Talk. We also, that's about it, but we have this as approach that would go with Allen Bradley. If you want to use it, go to chapter 15 and see how it's set up, but it has some crude peculiarities to it. Once you get used to it, it's okay, but to get started with it is pretty cryptic. It's the older style of programming the HMI that was used before they brought along the view, but it's harder. Now, if anybody is interested in HMI and really interested in HMI, and you want me to get you set up with it, I have some extra old computers, and I can run the program called, I can get you the program called Ignition. And I have 7 licenses for it. So I can actually give you a license for that, and you can run that. It's a very popular package today, but just getting started, it doesn't matter. But if you are interested in HMI, big time, and that's what you want to do your major effort on, I do have a license for 7 of those. Everybody understands that you can go down through here and pick off both Allen Bradley and Siemens and get 2 and 2, so you get 4 points. Not just 2, you can get 4 points on these guys. Okay? All right, so we were in chapter 6. And I want you to understand that chapter 6 is probably the most, I think, the most thoughtful chapter that I have. Chapter 11 is the most heavily trafficked chapter on the web. Um, I've told you that before, but chapter 11 is the most heavily trafficked, and I'm kind of disappointed because I think chapter 6 ought to be the most heavily trafficked because it's a chapter that's got more stuff in it than just about just about any other chapter. But for some odd reason, chapter 11 is the one that people think they need. And when we get to chapter 11, I'll give you some reasons why it is heavily trafficked. But honest to goodness, I really don't know why it's heavily trafficked, but it is. All right, it is. It is. It is the chapter that more people go out and look at than just about any other ones. Okay, so again, uh, I I don't get paid. This is not a money-making venture for me. It was a defensive move by me a long time ago because when I first started teaching this course, I was very dissatisfied with the texts that they had. And this chapter is one of the chapters that really came to mind because you can teach how to build a circuit, but when to build a circuit, they don't teach. And that's the hardest part is when do you when do you do a memory circuit? When do you have an epiphany that this is a memory circuit that I need to work with now, as opposed to something else? Okay, so it's more of when as opposed to how. All right, so I want you to understand that this is a course that tries to answer the how as well. All right, so basically, I started talking about one shots the other night. We're going to start talking about one shots here. But when you're programming, if you need a switch, but there is none, you don't have one developed, there's none there available, then think about making a memory circuit. Okay? Best advice I can give you, if you come up to a wall and say, in the program, I need a switch, but there is not a switch available and nobody's providing it, and you really think about it and you think, well, there's certain circumstances where a switch wouldn't work, but I need that switch. That's when you start thinking about building a memory circuit, and that's pretty much a very good rule. Okay, so that's that rule. That's, I guess, a basic rule. Then I talk to you about this idea of one shots. Okay, so a one shot is it looks like this. If you're looking at a button, here's the button. You push the start button or something like that, and it stays on for a while, and then eventually it turns off. So that would be a on signal, okay? So it would do something like this, a signal that would at some point in time turn on. A one shot would be a bit that comes on for one scan. If this is one scan's worth, it's one time around your program, okay? It's on and then it's off again. You'll never see it on the screen of, I'll never say never, but very, 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 very rarely will you see it actually blip on the screen. It may, but you probably won't, you'll say, now what was that? Okay, and you'll miss it. So it's hard to see these. So you will not be able to see these on the screen, but they come and they go right away. Okay, now what makes a one shot work? Well, when I started programming, I did not start programming PLCs. I started programming real-time computers. Okay, so the first 4 years of my work in industry was not working with a PLC at all. it was working with a real-time computer in assembler, okay? So factory floor applications using assembly level programming. And you say, how much was that computer and how many bytes was it and all that kind of stuff? Well, it was a $100,000 computer, okay? It had 16K of memory, 16,000 16-bit bytes, or 16-bit words. 16,000 is all it had. Of that, half of it was used by the operating system. So I had about 8,000 words to use to program with. I had to be very frugal. Anyway, most of the applications that I programmed, you ask the question, what is it? What was it last scan? And if they're different, do something. Okay? That's all it was. And so everything I programmed with one-shots. Basically, a decision was being made based on what's happening now, what was the last time through the program, which was maybe 15 milliseconds ago or whatever. I think I ran that program that I was talking about every 8 milliseconds. So every 8 milliseconds, the program came in and did its job. So what is it? What was it 8 milliseconds ago? If it changed, is that something that's important? On the leading edge, you make your move, and you're at a program that goes off and does something. Easy. That's exactly what we did. Okay? Now, that is not what they do most of the time in PLCs, because like I told you before, a PLC looks at signals predominantly. That's what it does. It looks at a signal and then it tries to do something on that signal. And I told you that when you are looking at a seal circuit, and they're looking at a seal circuit, and you walk up behind the person that's looking at it, and they're having trouble with it, but they've isolated to the specific seal circuit, ask the question, should you make the start part of that seal circuit a one-shot? And they may look at you like, who are you and why are you saying that? But it's kind of like what I said, salts on your hamburger or something like that. If it tastes flat or whatever, you put a little salt on it. Well, this is a kind of a signal that sometimes you introduce, but what do you have to do in order to make this work? Well, you have to supply a separate bit for what we call the last scan bit. So here are some examples, okay? And this is an FBD, and I'll show you one this is one in ladder. So this is a set reset. This would be this would be the Siemens memory circuit. So if you were to do this and you were talking about Siemens, you would say, okay, now if that's what you said, instead of making this just the start button, you would make it the leading edge of the start button. How do you do that? Well, you use the start tag, and that would be the tag for the input, but you also have to put this other bit in there. And what does this bit do? It's the status of the last scan. It's the status of the last scan. Was it on last scan? Is it on this scan? You follow me? If it was on last scan, but it's off, if it was off last scan, but it was on this scan, let it go. If it was on last scan and it's on this scan, block it. That's what that says. Okay? Does that make sense to everybody? Now that's what it is. All right, so this is a wasted bit by most standards. This is a bit that is just there. You have to supply it. It has to be unique. You can't double use it. You can't use it for 10 different things. You have to use it just dedicated to this one thing, but there it is. That's the last scan status of that bit. And it blocks after one try. After the first time, it sets after one try, and then it blocks from that point on. So you get this leading edge signal. Does that make sense? You say, why does that matter? Well, here's an example of it mattering, okay? All right, so you have a sequence of things that happen. Okay, so this would be a, well, okay, so here are events, okay? Is event number one, event number two, event number three. Event number one, event number two, event number three, event number one, event number two, event number three. All right? As long as these events do not overlap, you can say, which was the last one that turned on? Right? Which was the last one on? And this one, if you're in this period of time from here to here, this one was the last one that turned on. If you're from here to here, this one was the last one to turn on. If you're from here to here, this one was the last one that turned on. But if they overlap, guess what? It don't work. Everybody follow that? It does not work. So if you have overlapping signals, now all of a sudden, which was the last one to turn on? If you have two that are on at the same time, either one can be the one, and it can mess you up royal. So what must you do in a situation like this? You must revert to the leading edge signal to say which one was the last one that came on. And if you don't believe that, go to chapter 11, work the pump problem at the end of chapter 11. Work that problem and say, don't use leading edges, okay? Just ignore the leading edge. There's a hint in that. I actually tell you how to write that program. There's a step-by-step hint of how to do it. Don't use the hint. Don't say, I need a leading edge. Just say, I just need the signal of which was the last one turned on. You will never get the thing to work. But if you use the leading edge, it will work, okay? So if you don't believe me, there's an example, a biggie, that will cause you to either get that program or not get that program, all right? But again, sometimes it doesn't matter. Sometimes it really matters. And again, you decide. That's why they're going to pay you. Okay, now here is the Allen Bradley approach. One of the Allen Bradley approaches. Here's one of them, which I will never use this one if I can help it. I will never use, never say never or always, but I hate this approach to Allen Bradley. What's the difference between Allen Bradley and everybody else? If Allen Bradley didn't think of it, and they thought of a lot of stuff, but if they didn't think of it, they're not going to give credence to what somebody else thought of. Who thought of doing it this way? Thought of this little right there. Wasn't Allen Bradley, it was Modicon. Everybody else but Allen Bradley accepted this nomenclature for a leading edge, but not Allen Bradley. They made their own way of doing it. And by the way, before we had this, could you get a one shot? Yeah, you could build a one shot. You only had to do this. And this is, we did this until, there was a day before, when dinosaurs still ruled the world, that we did not have leading edge and trailing edge one shots. Believe it or not, that was not part of the PLC program. But we built them ourselves. And I'll show you how we built them, okay? So you would do something like this. Here's my signal, here's my I, and it would go to a bit called A, okay? Here is A, and it would go to B. All right? Everybody see this? This happened, this is your last scan bit. This is your bit. So you would say A, but not B, and what do you have? A one shot. It's the same thing. Does everybody understand that? This is a scanned program. You execute B, and then you execute A. B is set before A, and then you come down to that other thing, and that other thing is, oh. So B is the one scan delay of A. Make sense? It's exactly what you do. And that was done without having these kind of things come along. But then they came along with these kind of things. Oh, okay, that's a one shot. It's hard to identify this as a one shot, even though that's what it is. Okay? But Allen Bradley, everybody, I shouldn't say everybody, but you know what I mean. The vast majority of the PLC vendors, when Modicon put this little P or the up arrow in or the little N and the down arrow in, everybody got the idea, okay? And they followed suit, including Siemens, including TI and a bunch of other people, okay? By the way, TI, Texas Instruments, at one time had a programmable controller division. I bet you didn't know that, right? They did. Who bought them out? Siemens, okay? So other people have bought other people out, all that kind of stuff, but Siemens actually is the one that owns what's left. There's nothing left of TI anymore, of the programmable controller division, but they had a very popular programmable controller. As a matter of fact, in the overall scheme of things, the 5TI programmable controller from Texas Instrument was the first programmable controller to break the $5,000 cost barrier. And they were used everywhere. Everybody was able to use a 5TI because they didn't cost very much money. A typical programmable controller costs between $30,000 and $50,000 in the day. If you wanted to find who the Modicon salesmen were, look for the Mercedes-Benzes in the parking lot. They made a potload of money. Salesmen for Modicon were it was hard to get a job with Modicon, but those guys were extremely rich. They made a potload of money in the day, in the 70s and 80s, early 80s. And then Allen Bradley took over, and Allen Bradley cleaned their clock in the United States. Okay? Modicon's really a has-been. They're really nothing as far as innovation, all that kind of stuff. Siemens is out to clean Allen Bradley's clock, and I don't think they're going to do it, but on the other hand, you talk about people that do not like each other. You talk Siemens to Allen Bradley, or Allen Bradley to Siemens. And that's why this book will never get sold. Nobody from Siemens will ever support a book that's got Allen Bradley in it, and nobody from Allen Bradley will ever support a book that's got Siemens in it. So it's never going to get sold as a book. But it has both of them in it. Hopefully you understand. It's better, I think, to have the book out there than to basically say that. Okay, so basically there's the P. Everybody see the P in there? That's the contact with the P in it. That's a positive edge. Leading edge. In is a negative edge. In other words, when the signal goes off, one shot, it passes power for one scan. Now, this is the Allen Bradley approach. Now, what does this do? What does OSR stand for? One shot rising, doesn't it? OSR stands for one shot rising. Is that my one shot bit? Nope, that's not my one shot bit. That is my blocking bit. This is the salt you put in the little circuit that basically says what? This is where you put it. This is my stop bit. This is my start bit. This is the one scan delayed bit by Allen Bradley. So it's kind of like put a little bit of salt in there. If it doesn't work, put the bit in there. Put that one shot bit in there. OSR or ONS, one shot. ONS, one shot. But it isn't the one shot bit. What is it? It's the blocking bit. It's the one scan delayed bit. Okay? Does that make sense? You must declare this as a separate tagged bit. But it works. It only lets power go down this leg of this circuit one time, and then as long as this is on, and this is on one scan delayed, then it blocks it. So it only allows power to go down this leg one scan, and then this blocks power to go this way again until it turns off, and then when it turns back on, it does it again. Okay? Simple. This is your one scan delayed bit. That's all it is. Totally confused? Don't be. You use them when you need them. I am a one-shot happy programmer because I learned everything should be a signal, leading edge, make it a one-shot. Every single thing that I can do, I make a one-shot. You say, well, that's a waste of a bit. I don't care. That's why, that's why they gave us all these bits, because to use them. So I do this almost across the board on every memory circuit that I have, just about. Okay? If you don't believe that, go to the program at the end of chapter. Okay, I'm going to show you a program that I wrote. I purposely don't write many programs to put in here. I can show you programs that I've written, and you can come and look at some of them and say, well, that's kind of neat, or that's kind of dumb, or whatever. But I want to show you one that I wrote, and I'm not proud of this, or I'm not like this is the greatest thing ever since sliced bread. But this is a program that I wrote. I'll show you one. Okay. Okay. So and up until this semester, up until this year, I ask you to write this program, and this is one that you can type in for free and get 4 points for. And we've had people that have tried to type this or tried to do this program, and they've struggled, to say the least. It's not an easy one, but again, I want you to understand that I don't write many of them, but I do occasionally. Well, I'll get there someday. High school Rubik's, okay? Down here under text, all right, so here on week 6, page 52, is a program that I wrote. Now I want to show you how many one-shots there are in this program. Okay, here's the start. The actual program is as follows. There's one. You start getting an idea. Not. There's one. Not. Well, I take that back. There's quite a few, but not everything's a one shot. But there's a lot of them in there. Nope. Anyway, you get the idea. I use a lot of them. That's, in my opinion, that's a lot. It's not everything, but there's quite a few of them in there. Now that is the program that is at the end of chapter 13. One of the programs that I ask, if you want to write it, you can. And I give you the old way of doing it, but in chapter 13, I do not give you that program, but for the Rubik's Cube people, I gave them that program so you can borrow it from the Rubik's Cube people, type it in, and get 4 points. It's a worthwhile program to actually type in because it does have a lot of parts and pieces to it. So it is I think it's a good chap. It's a good program to get to run, and you can do that. And you can also get that from, I think you can do it in Umbrella. It's 4 points and 4 points. It's 8 points altogether if you do it both ways. Anyway, so that gets you through one shots. Now, the heart of this chapter is, like I said, not how to build a memory circuit, but when to build a memory circuit, okay? When to build a memory circuit. And this would be a case in point. When you're doing this thing, this juicer problem, you find out very quickly that there's 3 stages. There's when you push the button to run, and then there is the fill, there is the condensing stage, and then there's the drain stage. Okay? And these are mutually exclusive. Now we talk more about state diagrams and moving from state to state to state in chapter 11. But I want you to understand that this is the boss. This is the one that says, I'm running. If you like Venn diagrams, this is the big running circle. This is your Venn diagram. Okay, this is everything. This is the world. And then you have it divided into three parts. You can have the fill part, the fill part. You can have the condensed part, and then you can have the drain part. Okay, so you can be in this stage, you can be in this stage, you can be in this stage, and you move from this to this to this. Okay, which I show as memory circuits. They're mutually exclusive. You are running when you're in this stage. You're actually doing the operation, but under this big all-inclusive everything, you can be either doing this, then you move to this, then you move to that. All right? Now, that's a hint of how to write circuits, but I'm going to give you some overall thoughts now about how to set up a memory circuit. So these are some of these are some things you have to think about, and you might have already figured all this stuff out, you might not have. So here is a statement about how to run conveyor C1, okay? So I want to run conveyor C1, okay? I want to run C1, all right? Now, you can say here that if you push this button, you put a box on here, it's going to run down here, and it's going to go by that photo eye, and then it's going to stop. So you would typically say, I push the button as my start, and then C1, and then the photo eye, the trailing edge of the photo eye, and then you're done. All right? It's not really the trailing edge of the photo eye, but you got the idea. It's something to do with the photo eye. It's something to do with the photo eye. It's not the trailing edge of the photo eye, but it's something to do with the photo eye. When the photo eye goes on and then turns back off, that's when you want to do it. We'll fiddle with that later, but that's not the right signal, but it's close. It's something to do with the photo eye turns it off, okay? Now, I put another restriction in here, though, when I say this conveyor C2 is running or not running based on another person writing another program someplace else. And I cannot run this box onto conveyor C2 without conveyor C2 running. So I have a contact off of C2 running that says it's running. So this is the actual contact for C2 running. So hopefully you understand that the real logic is not this, it's something like this, which says, please run. So this is an internal bit that says, please run, all right? And only when you are saying, please run, and C2 is running, do I run C1. So many times, the internal bit is not an output. Get over the idea that all my control bits have to be outputs. They do not. And as a matter of course, most of them aren't. Most of my output bits come as output, as logic after I've built my internal logic for control. So the thing that actually runs the show is this bit right here, which is nothing more than a please run conveyor C1. Everybody follow that? So you walk up here, you push a button, you say go. It may go, it may not go. If this conveyor here is running, this one will run. If this conveyor over here is not running, it won't run. But as soon as this one runs, this one takes off and runs until it clears that photo eye, and then this one will not turn back on until you push this button again. Does everybody see that? It's a memory circuit. And by the way, has this circuit ever been designed before? Is this a real circuit? You betcha. This is right out of a circuit that I designed in Jackson, Mississippi for a ceiling tile line for Owens Corning fiberglass, okay? Not exactly, but close. It's the exact same. We talk about this circuit multiple times, but this is one example of it, because it does bring up some very interesting points. Okay? And here is the photo eye bit that actually turns that bit off, is this bit right here. Here's another one. Now, I've got you all trained to see if you see a bin or a something with a high and a low level, what do? You write a memory circuit for it, right? Why? Because it has to be satisfied. If this goes low, what happens? You ask for more and you ask for it until it goes to high. So basically, there's something, you're using up material out of this bin to satisfy something. We don't know what it is. It might be a process that this is the only product that goes to that line. We might be making pancakes and this is the flour. I don't know what we're making. You get the picture. It could be anything. And this is waffles and this is pancakes. I don't really care. But we're using out of this bin, for two different lines, okay? Now, when it goes low, you want to say what? Fill, right? So how do you do that? Like that, right? So low does the job and high turns it off. And that would be fill one, right? Fill bin one, right? Except for the possibility that you could already be filling bin two. And if that's the case, what do? You block fill one if fill two is on. And you do the likewise for bin two. These are competing resources, right? Fill bin two. This is my low and my high for bin two. And this would be my, if I'm filling one, I do not want to fill bin two. Now, are these running any physical devices? The answer is no. They're not running anything. What's running this thing right here? This is a conveyor going forward and backward. That conveyor is running to the left, conveyor to left, when I am filling bin one. So when I'm filling bin one, I am running conveyor to left. Okay? And that is a physical bit that turns that motor on in that direction. All right? That's a physical contact that turns and says, run to the left. Fill bin two is a physical contact then that runs C2 to the right. You see, these are not physically tied to any actual output device. You follow that? But they set the whole thing up, don't they? They set up all the logic that you need. And then how do you run this little screw conveyor? And by the way, I hate screw conveyors. You should hate them too. They're very dangerous and stay away from them. Please do not, if you're a mechanical engineer, do not design them unless you absolutely have to. If you're a mechanical or electrical engineer, stay as far away from them as you can. They can hurt you and they can take your life, or not your life, but they can take your arm, your finger, your hand, anything, okay? So please, they're very dangerous devices. But if you're going either left or right, which is this or this, whoops, I can't do that. Well, I did. I just did, didn't I? Well, anyway, you get the idea that this is my screw conveyor. Either left. Now this up here is a totally separate entity. It would just be one fill. That would be a single coil circuit. This one does not have any competing devices, but this one does. All right? Does everybody see that you can do this? And if you have a stepping program, you can do the same thing with that. Now, this is important because this is a chain of I want to show you a chain of memory circuits. Okay, so not a chain of memory circuits, but how this one memory circuit can set up a chain of events. Okay, so how would you write this? What is this? You have a coal mine out in the back someplace, okay, in West Virginia, and then this conveyor feeds this conveyor feeds this conveyor feeds a car, a car on a rail, right? Does that make sense? So how do you start this? Push button says fill, right? When it's low, when it gets to high, it turns off. Does that make sense? So basically, you would do this. You would say low, and then not of high means would be to run. So this would be low, and not of high, that means to run. Okay, now that gets you started. But what does that really do? That says turn on conveyor C3. Now C3 and not high level, in other words, if you run a high level here, that means you've overflowed this. So C3 and not high level 4 runs C2. And then C2 and not high level L3 runs C1. Any questions about that philosophy? Now that is not a full circuit. You need timers in here as well. And we're going to talk about timers in a few minutes. But why would we have timers in this circuit as well? Well, if you have a switch that goes high and low and 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 high and low, you're turning on a motor and turning it off in rapid succession. All right? If you do that too much, you will basically tear up your motor. If you start a motor too many times per unit of time, it will effectively make your motor get overheated and destroy the motor. So what you have to do is you have to say, once it's tripped this thing, you have to wait maybe 30 seconds or a minute or 2 minutes before you let it turn back on. Let the motor cool back down. We're going to talk about timers before we get too far. But does everybody see that this is a chain of, and maybe you've all figured this all out, and you don't need me to tell you how to write a circuit like this. But basically, what are you getting from this? What are you getting from this chapter? A lot of practical little programs, little bitty programs. But what are big programs made of? A lot of little ones, just like this. And then other things as well. It gets more sophisticated. But a lot of stuff that you will end up doing is sort of, as I would say, kind of mundane, but it's like this. All right? And this is not to say that it's a mundane job. You have to do this kind of stuff in addition to all the other stuff that's really neat and that really takes a lot of time and it really costs you a lot of energy to do. But this is the kind of stuff, this would be something you'd say, I can do that in 5 minutes. Yes, you can. You can write this program in 5 minutes and be done with it. There's other parts of the programs that will take you a lot longer. But this is the kind of stuff that you can write fairly quickly. But I want you to understand that a lot of the things that you do is built on this. By the way, where are the Winter Olympics being held this year? Italy. What town? It's close to Milan, isn't it? Turin, Turin, is that the town that they're in? Is that the town that they're in or not? Does anybody know? I haven't been watching them, but the Olympics are going on right now, right? What town are the Olympics in? Milan? Isn't the town Turin, Turin? That's not? Ford has a plant, or they had a plant in Turin, Turin, okay? Ford Motor Company had an engine plant in Turin, and they may still have it. They used to have Modicon program controllers in that plant. They never printed off listings from those program controllers because they were too big. How tall or how long or how wide measurement in feet, how big of a listing would come off of one of the engine PLCs that would be printed out, a printed listing of a PLC in the engine plant in Turin, Italy for Ford Motor Company. I know this for a fact. The guy that worked there told this to me. 22 feet tall. A listing for a program in a program controller. 22 feet tall. All right? All that said, that's a big program. Everybody agrees that's a big program, right? What are big programs made of? A lot of little programs like this, okay? But you see why people pay a lot of money, and in the United States, the people that did this work are all either dead or retiring. So there's nobody other than people I'm looking at right now who are picking up and doing that kind of work. Believe it or not, you're a rare commodity. You're a rare species. You're very rare. And if you even like doing this at all, to consider doing this is commendable. But to be faced with a program that's 22 feet tall, a listing that's 22 feet tall, and be able to go in there and make changes to it, that says a lot, right? And I'm sure they've reduced it today and they've done AI to it and they've got it down to about this tall or whatever. I'm kidding. I don't know what they've done, and I don't even know if they still got a plant in Turin. But again, that's the kind of things that you can get into. The complexity is there, but what are these big programs made of? A lot of little programs like this and more, but this is part of it. All right? Anyway, now if you haven't figured it out yet, I like stepping programs. All right? I love these little programs that go back and forth or whatever. So this is a program of sorts. Now, and by the way, you may ask the question, what is he going to ask on our test? I offer you example 1 right here. This is the kind of stuff that you will get, variations of this, but this is the kind of stuff you're going to get. Okay, write the program that will make this happen. In other words, you push the button and it goes once across. When it's halfway across, you see a photo eye and it turns on and sprays. And it sprays until it gets to here. When it gets to here, it turns back and it goes back and it stops. All right, there you go. How do you write that program? This is a stepping program. So you're going down to here, and then you're turning around and coming back to here. Now, I know at the end you have to have a timer. You have to put a little timer in here, so we're not worried about timers yet, but we will talk about them. But here you go. So how do you do this? Everybody follow that. So you identify that you're going to the right, and then when you hit the photo eye, you turn around, you go to the left. And when you hit the photo eye at the left, you stop. How do you do that? How would you start? You start with the all-inclusive run cycle, right? Run, right? You're either running or you're not running. Everybody agree with that? Everybody say, I see what you're saying, because Venn diagrams, or how many of you like Venn diagrams? Does anybody like Venn diagrams? Not a few. Okay. I'm kidding, but you got the idea, right? A Venn diagram, it's the all-inclusive run bit, the run bit, okay? So if you're running, you're making this happen, and if you're not running, it's setting idle. So that basically is yours. Okay, so you start. Everybody agree with that? Always put that in. I hate to say always or never, but this is as much of an always as you're ever going to get. When you hit the button, set something that says run. Now, when you have that run bit and you do this, you should set a bit that says what? To the right. And you seal it. And I don't know what's going to stop this. Oh, and by the way, you got to put the run bit in there too. You got to put run in there. Always put run in with us, all this stuff. All right? Everybody figure that out? Now, when you get to the right, when you say I am running, and I am moving right, and I hit the right photo eye, what do I do? Move left, run, and move left, starting or a leading edge, move left, seal, and I don't know what's going to stop it yet. This is move left, please. This is move left. Okay? And then what stops it? Move left and right photo eye is a stop bit. And I can go up here and write stop, 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 and every one of these circuits and I'm done. Except for the fact that I have that little other one that says I'm moving to the right and I'm spraying. So basically, what is that? There's another photo eye that says I'm moving to the, I'm running and I'm moving to the right. And I hit the photo eye and I don't know what, okay, and this just says spray. I don't know what's going to turn this one off. Yeah, I do. I know what's going to, it says spray. And then what turns it off is the right photo eye. I'm kind of crude with how I write it, but basically got the idea. Any questions about stuff like that? Make sense? Piece of cake? You should be able to do this. Maybe not right this minute, but think about it. And you should be able to write this kind of a program. Because this is the nuts and bolts programming that you will end up doing. And now there's more to this than just this. We get into some of the later chapters in this book, and I call them the big box chapters, like Menards and Lowe's and places like that. But they get very complicated in those chapters. But for the most part, you can stick with these circuits and do an awful lot, and then we get into some of that other stuff as well. But in those chapters, you still go back and you use this kind of logic. Okay? So the big box chapters use this kind of logic in addition to other things. And that's about it for chapter 6. We don't have a lot of time for chapter 7, but we're going to talk about it anyway, just a little bit. By the way, this is a page out of a book from the German stuff. And this is the program that they write. This is German 101 programming. And it includes words like, I forget some of the words that they use, but they use some Words that we've never seen before. Anybody know the German for Abgenben? I don't know what that means. Anyway, this was a book that was supposed to be written for the English language for English, but they still got German words in it. But that's an example of a Siemens program. What do they have in it? A bunch of set resets, right? A bunch of set resets. And I bring that up because why? If you were to roll out a program from Germany, this is what you would see. If you roll out a program from the United States, what would you see? Seal circuits. That's why I write with seal circuits, because why? The American industrial, I hate to use the word complex, but the American industrial system more likely accepts ladder logic with seal circuits than they do with set resets, because the electricians in the United States have been trained to use seal circuits. Now, if you found an electrician in Germany, I bet they would just love these circuits right here and say, yep, that's exactly what we do. That's exactly how we do it. And yet on we go. But in the United States, this is what you see. That doesn't mean you can't program like this. You can program like this. It's just you will be hampered by people in the United States that will basically say, well, can't you program like I program, or like I like to program, or whatever? And this is the way most American electricians like to see circuits. Now, it brings up an important point. What's your goal, or what's your ultimate goal in writing programs for the factory floor? Is it so that you can be the maintenance person that comes back and maintains these programs for the rest of your life? Do you want that job? No. Thank you. You do not want that job, right? You want to create, you want to get it up and running, you want to be a teacher for a few days and explain to the people what you did and how you did it. And then you want to walk out with your head held high, and you want on the next job. And you go to the next job, and you go to the next job, and you go to the next job. That's what you want, right? That's the goal. You do not want to have to be the maintenance person that has to come back and maintain this stuff, because you'll never walk away from it. You'll be constantly being hassled by it, okay? That's not your calling, I don't believe. Okay? All right, enough on chapter 6. Chapter 7. I know I'm about 2 seconds from being kicked out of here, but let's just look at chapter 7 just real quick, and then. Okay, so what were the primary things that a program controller had to do from day one? You had to be able to create logic that was like what they had with relays, right? But you also had to have timers and counters. And I've already brought up to you a little bit of why timers are so important, but I'm just going to say this, that anytime you go to the end of travel of a cylinder, or any kind of end of travel of some kind of a device, if you don't stop, delay, and then do something else, you're going to tear up your machine. Okay? So there's a slight delay every time you shift from one step to the next, to the next, to the next. There's a delay in there. And those delays are timers. You use timers to do that. And at one time in this country, there were people who basically roamed the factories of Detroit, and most of those factories have closed, I understand that. But they made parts. They made a lot of parts, okay? And they made money by lessening the time gap between steps. So if you can if a machine makes 8 million parts in a year, and you can make 8.2 million parts in a year by making the time delay between steps just that little bit slower or a little bit greater, you can justify good salary money, and people made a lot of money doing that, bringing these timers down to exactly the least amount of time between steps, and they would be able to do that, and they made a lot of money at it. Okay, I was never interested in doing that, but on the other hand, that's what you have two things working. One is you want to make it fast. The other thing is you want to make it so that you don't shut down. You can't shut down. So you have this point at which you get it as fast as you can, but you can't go any faster than that. All right? Now, here is a pneumatic timer, and it had a relay part to it, and it had a dash pot on top. The part on top, you'd actually hear a click and then a like a little exhausting of air, and then a second click. They weren't that accurate, but they were accurate enough. They would give you maybe a second and a half, or 2 seconds of delay, which is enough time that you could set these things up. Now, on a rainy day, they might be a little bit slower, a little bit faster. On a stormy day, they might be a little bit whatever, maybe low humidity, they might be a little bit different. They might act a little different, but that's okay because you didn't really care. The bad side of this was it cost a lot of money. Another bad thing about these was if you got it wired, if you needed an off delay instead of an on delay, the head was not, you had to take it off. You couldn't flip a switch. Like, you think, well, you should just be able to flip a little switch in there and it goes from an on delay to an off delay. Doesn't work like that. You had to buy a different head, rewire it, and an hour later, 2 hours later, you would come back and have to start it all over again. So if you missed on your application, it was painful, very painful. And they cost a lot of money. And I'm going to bring up one more point. This is the schematic for one of these kind of timers, okay? This is an on delay, this is an on delay normally closed, this is an off delay and an off delay normally closed. If you think about this is pointing upwards, you're living. This is pointing downwards, you're dying. Okay? Now, I bring that to your attention for two reasons. One, because it's easy to remember, but that's the old schematic way of doing it. That's not what you see on a PLC, in a PLC, but that's the way that the old schematic would draw this. The other one is because I started as an engineer at Libyons Ford in 1971, and I didn't know spit. I didn't know anything about any of this stuff. I thought those contacts were capacitors. I didn't know anything. And people came up to me, a few, not a lot, but a few, and they befriended me, and they gave me hints, and they gave me little tidbits. And one of them was named as Jim Nenke, and I'll never forget him coming up to me one day and telling me, the one that goes up is going up, and that's the on delay. The one that's going down is going down to the earth. It's dying, and that's how you remember them. So my point is this. You will have mentors, believe it or not, in your job. You'll have people that will help you, and take advantage of it. Don't expect anything from them, but please do not pretend like, well, I know more than they do, because they're going to know some things that you have no clue about. I've got more stories about that as well coming later in this course. But mentors are important people, and I'll never forget what he said that day. And it was, as a friend, he told me something that I had no clue about, or why it was important. And it just stuck with me, like, yeah, that's a nice thing. And you can maybe be a mentor to somebody else. I consider me being a mentor to you in some of these cases, but I also know that, you know, I'm giving you a grade, which makes it a little bit different than being just a mentor. But a mentorship is a very important thing. Have mentors, be a mentor, make sure that you pass along stuff that you learn, okay? Enough on that. Jim Nenke is a good guy. Anyway, so we're about done for today, but I want you to understand that we can go through this whole chapter and you can get all involved with this. I live and die with one timer, the TON timer. There's another one we'll talk about a little bit, but TON is my only timer that I'll ever expect you to be able to remember. I can't remember all the other ones and what they all do. You don't need to remember everything in these cases because you can get along with a TON timer for the most part. And there's one other one that I'll talk about as well. But the TON, as you're reading through chapter 7, please do not get over enamored with all these different types of timers. You can live with one timer for the most part, and that's the TON. All right? That's about it. Do I give you a quiz this week? Probably out of chapter 6. Now we're moving into the stuff where I can actually ask you some really good questions, and this chapter 6 questions are probably a good one to start with. So that's probably, I will do that. I hate to give you a quiz now after I goofed it. If anybody wants their quiz 3 back, you can. Otherwise, they're going into the trash. Did everybody get their stuff? Did everybody get what they handed out? Whatever.